Good morning, Astronomy 1020. Welcome to Lecture 3, Part 2, and Homework 3. Today, we will be exploring the key works of Sir Isaac Newton. We will be learning about forces, we will learn about gravity, and hopefully we will improve our understanding of planetary orbits and stellar orbits. Today is going to be mathematical if I do it right. We're definitely going to need our Casio calculators. Can you guys show those to me and make sure that I'm going to have some punchers here today? You guys got these handy? So important. And Caitlin, you got yours? Okay. It's very important when we do some exercises. Amanda, you got one too? All right, Amanda. Yes, I'd like to see you. Okay, very important when you're following along with me that you punch these numbers. Okay, so let's not waste any time. Today, we're starting off with some keynotes on Newton's laws of motion, and then we'll move on to gravity. If I didn't mention it last time, all of these things were written in the 1600s in Isaac Newton's great work, the Principia Mathematica, I think, and famous legendary book. Many of the things that were written in this book were a refutation to what is perhaps the first physics textbook, and that's the one written by Aristotle. Aristotle wrote a book called Physics, in which he tried to explain simple everyday things in terms of rational logic, things like why an arrow flies through the air, or what happens to a stone when it moves along the ground. And in some sense, that was very profound because it was the first time in human history, at least that we know of, that someone tried to record down observations about motion and how motion should work. And so he kind of started this thing that we do called physics. But some of his ideas were faulty. They were not correct. And they propagated through time in a way that led to lots of confusion. Isaac Newton solved that confusion by giving us good judgment about the motion of bodies. And at the end of our last lecture, we learned a little bit about the difference between velocity and speed. We learned a little bit about acceleration, and those concepts are critical for what you're about to learn. So I hope you watched or were here for that video. So let's do a little bit on Newton's 3 laws of motion. These are a science classic. And in some ways, all 3 of these laws, what they're really about is they're about defining what a force is and what it does to change the motion of a body. So the first law is the law of inertia. The law of inertia states an object in motion tends to stay in motion unless acted upon by an outside force. In other words, forces are things which change the motion of bodies. Another corollary to this is an object at rest tends to stay at rest unless acted upon by an outside force. I believe Newton expressed it in both ways. This was an important statement to make because Aristotle had some confusing ideas about motion and gravity. Aristotle claimed that, let's see here, if you took a stone and you sort of pushed a stone along the ground, or if you rolled a stone along the ground, it would eventually come to rest And I think his description was a little bit seductive because he said, well, the natural state for bodies to be in is to be at rest. And since he was a geocentrist and he believed Earth was the center of the cosmos, he believed the center of Earth was kind of the natural resting place of the universe. So his idea was, if you slide a stone along the ground, it will have gravitas trying to pull it down, and it eventually comes to rest because it's trying to pull itself down towards the center of the Earth. And it almost sounds kind of good. Newton, however, realized that a stone sliding along the ground would be subject to frictional forces, forces which do not act up or down, but are acting side to side along the direction of the stone's motion. If instead the stone were suddenly to be found in outer space, and you were to give it just one little flick, it would begin to move, and there would be no interacting media, no forces pressing against the thing to stop it. And in that sense, it would travel unimpeded forever at some velocity. In other words, I suppose you could say that Isaac Newton had discovered the principles of the video game Asteroids, right? And if you've gone to your local pizza parlor and you've played Asteroids before, you know that you can sort of take this little rocket ship and you can rotate it around and shoot the asteroids. But that if the asteroids get too close to your ship, you have to press the thruster and you have to fire the rocket forward. But once it gets moving, it's zipping across your screen and it's hard to slow down, right? At that point, you can easily crash into one of the asteroids unless you rotate 180 degrees and fire some retro rockets. I suppose what's cool about Isaac Newton is that he didn't have asteroids at his local pizza parlor, right? He had to think this stuff up for the first time hundreds of years before anyone had Star Wars or video games or anything cool like this. With no experience of outer space, he kind of understood how things would work if you removed planet Earth and the influence of friction and other things. It's also important that if you take motion as a code word for velocity, and let's say we were to do that. Then forces are things which change the velocity of moving bodies. Okay, but what are forces? We still haven't really, gotten into the weeds on that. And that's what the second law is going to do. The second law of motion could be considered the definition of force itself. And it's actually a math equation, probably one of the two most famous math equations in physics, the other maybe being E equals mc squared. And it's force is equal to a mass times an acceleration, right? In other words, a force is what you need to take a mass and cause it to undergo an acceleration. To learn about a physics quantity, it turns out that the smartest way to do that is to study its units. And so maybe we could have a quick digression about units of force. That would require us to know our units of mass. Do you guys know what our units of mass are? Say in the MKS system?
Wouldn't it be grams?
Grams are a metric unit of mass, but they are not the units that we prefer when working in MKS units. And
kilograms.
Exactly. So let's make note of this. We're not just asking about units of force, we're asking about MKS units of force. So the mass would be in kilograms. How about units of acceleration?
Would be meters.
Meters are units of length.
Speed and velocity.
Those are quantities, those are concepts, but those are not units. A velocity can have a multiplicity of units.
Second.
Meters per second squared.
Say that one more time, please.
Meters per second squared.
Thank you. If you remember last or Tuesday's lecture, meters per second squared. To discover the units of force, what we do is we combine all of these units together. Now, if you have a kilogram by itself, that means kilograms is actually on the top of a little secret fraction, because anything can be divided by 1. So anytime you have a quantity that's just sitting around by its lonesome, think of it as in the top of a secret fraction. Meters are in the top of a secret fraction. Seconds squared are in the bottom. So the MKS units of force are kilograms times meters over seconds squared. And you don't have to say times, you just say kilogram meters per second squared. Kilogram meters per second squared is kind of a mouthful to say. So we define this as a Newton of force in honor of Sir Isaac. So the MKS units of force are the Newton. And 1 Newton of force is defined as 1 kilogram meter per second squared. Once again, conceptually, the easiest way to think about a force is to think of it as a push or a pull. Lastly, we have Newton's third law of motion. And I don't know what, I forgot what the zippy title for it is, but I can tell you the words. Mind if I erase the first law for board space, everyone? All right. Hey, Jordan, can you lower the temperature to 70 degrees? Sorry, it's getting hot in here. Okay, and the third law says that for every action being a sort of old-timey way of saying force, for every action, there is an equal but opposite reaction, where reaction could be code word for counterforce. The third law is actually the sneakiest and perhaps the most profound, but it takes a little while to understand all of the secrets that it contains. A basic idea about the third law is that forces always exist between pairs of bodies. You can't have a force in a vacuum. Well, you can have a force in a vacuum, but you can't have forces unless you have 2 interacting objects. So a couple of often cited examples, they're kind of silly, but necessary to explain Newton's third law of motion, is to consider 2 different situations. In the case of a rocket engine creates thrust, and it creates a thrust forward in the direction of the rocket's motion by sending some exhaust, some rocket thruster, which pushes backwards. Since the rocket floats in free space, when you push gas out of the back of the rocket thruster, in order to preserve that every action there's an equal but opposite reaction, it creates a forward direction and causes the rocket to move forward. Another goofy example is what happens when you press your finger against a brick wall. Usually, a finger is not strong enough to push over a brick wall, so you might exert a significant force on the wall, but if your finger does not undergo an acceleration, if it is stuck, then the only explanation for how there can be force and yet no motion is that somehow, goofy as it sounds, the wall must be exerting a counterforce against your finger, which stops it from passing through the wall like a ghost. And although this seems silly, there are lots of cool and ingenious devices and things that you can construct that make use of this rule, such as the A-frame that you might put on the side of a house if you were painting it or reshingling it, which just consists of a leaning board pressed against the wall. But when you apply a downward force on this sort of diagonal ladder, it creates a sideways pressure pressing you against the house. Anyone who's ever had to paint a tall house might know what I'm talking about here. Okay, now that we know Newton's 3 laws of motion, we can move forward and we can start learning a little bit about gravity. Probably the most important reason that you had to learn about this is just so that you could know what a force is, that it has a definition, and that it has very particular units. All 3 laws of motion were just about describing how forces push things or pull them and make them start moving around velocity-wise. Please remember that a velocity is a change in acceleration. I'm sorry, let me try that again. An acceleration is a change in velocity. So when you accelerate something, you cause its velocity to move. And there are 2 legendary formulas. I don't know if we'll ever need to use them or not, but they're kind of classics from physics, right? You guys know about distance equals rate times time. That kind of explains how a velocity changes distance. And there's a corresponding formula, velocity equals acceleration times time. And these 2 formulas are, in a way, symmetrical to each other. A velocity makes things travel over a distance with time, and acceleration changes the velocity with time. These aren't part of Newton's laws, but they're often used in conjunction with Newton's laws of motion and forces. Okay, so I'll just leave it there. I won't say any more. If you guys are comfortable, I'm going to erase and we're going to learn a little bit about the law of gravity. Sound good? Okay, got a lot of little chunky modules to do with you guys today. I'm erasing everything. Let's get on to some stuff where we can start using our calculators. Newton also developed his law of gravitation, and it might be a little bit difficult to get you into the background of how he did develop it. I guess you could read the entirety of the Principia if you wanted to understand that. But he also lays out the universal law of gravitation. It's called the universal law of gravitation because Isaac Newton was one of the first people to realize that the forces which govern the motions of bodies on Earth are the same forces that govern the motions of bodies in outer space. And that was a unique thought for the 1600s, because previous to that, people thought that the heavens were a magical place full of magical substances like ether, and that different rules applied to the heavens than applied to the ground. If you actually read about Isaac Newton, you can actually look up his hometown of Woolsthorpe, England. Let's type this in. And if you look up Woolsthorpe, England, the first thing that comes up is Woolsthorpe Manor. Isaac Newton's ancestral home stands today just as it did in the 1600s. And they even have an apple tree in the front yard, which supposedly was the apple tree that inspired Newton to develop his law of gravitation. And there were some similarities between what was happening in Isaac Newton's day and ours, in that when Isaac Newton was a student at Trinity College, the Bubonic Plague struck London, and all these people started getting sick and dying, kind of like our modern coronavirus pandemic. And at the time, no one really knew what the cause of the disease was. They thought it might actually be dirty city air, but it turned out to be rats carrying the disease, and mosquitoes were transmitting the disease from the rats to people. So if you were in a place, a city with lots of dirty rats, you were more likely to get the bubonic virus. So what do? They sent all the college kids home, just like we do today. We're lecturing and talking to each other from our bedrooms here over Zoom, because we're facing a similar pandemic. And Isaac Newton wasn't like us. I don't know about you guys, but I haven't used my pandemic particularly efficiently or profoundly. There was a lot of staring out the window, okay? Isaac Newton stared out the window too, but he did something. So he brought back to his childhood bedroom the works of Kepler and Tycho Brahe and Aristotle, and he read these things and he thought some deep thoughts. And he writes in his journal that one day he's looking out the window and he was occasioned by the fall of an apple. He saw an apple fall to the ground. And he said it had a profound effect because it inspired him to realize that the same force that pulls that apple to the ground must be the same force that holds the moon in its orbit. And hear me out on this. See if you can follow along with the logic. If we go over to our slideshow here, and let's tiptoe back to that circular orbit. To understand why the moon stays in its orbit is kind of a tricky business, right? Here in the center, we could imagine that this is Earth. So let's see if I can do this here. So here we'll have Earth. And then let's use yellow for the moon. We'll put a yellow moon up here, okay? Now, if you look at the direction of the moon's motion at any one moment, the direction of the moon's motion is tangent to the circle, meaning it's sort of has this instantaneous direction off and to the side. And according to Newton's law of inertia, an object in motion should want to stay in motion. That moon, the moon should want to carry on in a sideways tangential direction and continue in the direction of its current velocity. But it doesn't do that. If it changes its direction, that is also an acceleration, because a change in direction is a change in velocity. And so the question is, where is the acceleration coming from? Well, let's look at the motion of the moon. The subsequent motion of the moon is to travel along the arc of the circle. And that can only be possible if there's another motion. If there was a force or an acceleration directed towards Earth, then the combination of the sideways motion and the downways motion will lead to the moon traveling over here in its orbit. And now let's analyze it once again. Now the moon is stuck here, and presumably it's still feeling the gravitational pull towards Earth. But the gravitational pull towards Earth is in a down sense. It's perpendicular to the sideways velocity. And if there were no forces acting side to side on the moon, it should still maintain that sideways component of velocity. It should not have anything pushing it side to side. So now you still have a sideways velocity, because nothing changed that, plus a downways acceleration, and the moon once again travels along the orbit. In some ways, the act of being in orbit is like constantly free falling towards the Earth, but having the Earth move out from underneath you or something, right? This is why people experience weightlessness or zero G on the International Space Station. It's not that once you get up 300 kilometers above the Earth, gravity stops working. It's that you're in constant free fall towards the Earth. And that's a type of weightlessness. Okay, anyways, orbital mechanics are somewhat complex, right? Okay, at some point, Newton developed a law of gravitation, and he discovered that there were two factors that really influenced how gravity was going to work. The first thing was mass, and the second thing was distance. Although in some ways you can say it's all about the mass of two objects. Now, eventually, we're going to write down the modern version of Newton's law of gravity, which is this. But don't write that down just yet, because I want to introduce it Newtonian style. Newton's version of the law of gravity didn't quite look like this. In fact, he wrote it out in words. But it did have as a starting concept that you would have two masses. They could be arbitrary masses, like the Earth and the Moon, or the Earth and the Sun. Hey, someone forgot to mute themselves, so I can... all right, let me find you. All right, you're annoying me. Somebody's annoying me. I'm about to call out an annoying person here. Let's find that annoying person. Carl. Thank you, Carl, for muting yourself. Okay. All right. Let's start with the concept. We have two large masses, and they need to be large because it turns out that gravity is a wimpy ass force. I mean, let's face it. These two markers here, they each have a mass of maybe 100 grams or something. But I don't feel any attraction between the two, and yet some must exist. Gravity is so weak that you don't really start to notice it until you build up a planet or a moon's worth of matter. So let's imagine we have something like Earth and the Moon. We'll call them arbitrary big mass 1 and arbitrary big mass 2. And we'll imagine they're separated by some distance, little d, which is always a center to center distance. And this matters, okay? The way Newton wrote his law of gravitation is he used this special symbol called a proportionality operator. Looks kind of like a Jesus fish. And this means proportional to. Our first homework problem is about using a proportionality operator. They're powerful symbols that work slightly different than the equal sign. Proportional to means it varies as. How does a quantity change? All right. So Newton's version, the one that he spells out for us in the Principia Mathematica, is that the force of gravity is proportional to the product of the two masses, which means m1 times m2, but inversely proportional to the square of the distance. And we're going to write out those words because they matter. When quantities are on the top of a fraction bar, we say they are directly proportional to the product of the masses. In other words, m1 times 2 are on the top of the fraction. Down here, he writes inversely proportional. Inversely means d is on the bottom. Inversely proportional to the square of the distance. And you guys need to learn these terms because scientists use this proportionality operator in a number of complicated ways all the time. They can quickly evaluate physical systems in ways that are not always obvious. Because our first homework is about using this, I want to try a couple of quick examples before we go forward. Can you guys write all that down so I can erase it? I'm going to erase now. Thank you, David.
Wait 2 seconds. Never mind.
You got to be quicker than that. One of the things about hiding in the back as a troll is I can't see your face. I can't see what you're doing. And it's hard. If I don't hear you, I'm trying not to have a lot of dead air on the recording, you know? So
Yeah,
Amanda,
well, this is what my eye looks like today, so we're hiding.
geez, I understand. Well, it doesn't look that
Mhm.
bad to me, but I hope it doesn't hurt too bad. Okay. Sorry about that, kiddo. I've had some funky eye things before, and it really, it's like you can't stop anything that happens on your face. You cannot stop thinking about or touching or messing with. Thank you,
I
David.
slipped on the ice.
Oh, really? Geez,
Yeah.
that's hardcore. So did you see that David put the words in the chat log, Amanda?
Oh my God. Amazing. Thank you.
Yeah, thank you, David. Thanks. Takes a village, right? Okay, I want to try a couple of quick, and you know what, Amanda, touche, you got me, all right? I want to try a couple of quick sample problems here before we go forward. Suppose I double the distance between Earth and Moon. The question would be, how does the force of gravity change? Or let's say, how does the force of gravity vary? And we want to know by what factor, by what amount. What we would say is, okay, I'm not changing the two masses, so they're not involved in the problem. I can just focus on the distance. The force of gravity is proportional to 1 over d squared. You always have to write the d squared. You always have to put the d on the bottom. And then what you do is you just substitute in the factor by which the distance changes. If you're going to double the distance is going to change by a factor of 2. So you simply write 1 over 2 squared. And that means 1/4. So you could say the new force is 1/4 of the old force. And that's a way of saying 4 times weaker. Amanda, let me know when you got that down.
I'm good.
All right. David, everyone good? I want to erase that. All right, one more sample question. See how this works. What if I instead say, suppose I double not the distance, but suppose I could somehow double the mass of both planetary objects. In this case, I'm not changing the distance, I'm only changing the mass. So I would write the force of gravity is directly proportional to the product of the masses. And here, each mass is changing by a factor of 2. 2 times 2 equals 4. So the new force is 4 times stronger than the old force was. This is how one uses a proportionality argument. You use it to figure out by what amount the force varies, rather than merely just calculating a force in newtons. It's a very powerful tool that I will try to show you the use of as we go forward. I don't have my standard kilogram mass here. I'm a little disappointed about that. I guess I could use these 2 ball bearings as a demonstration. I don't know what their mass is, but I happen to have these around, okay? When we have objects in space, like a planet and a moon or 2 masses, these are physical quantities that we find in nature. And we have decided how to measure them in units that we have imposed upon nature. for instance, let me write the law of gravitation again. Can I erase this? In the MKS system of units, we plan on measuring masses in kilograms. We plan on measuring distances in meters. And we decided that the good unit of force that we would like to use are newtons, where 1 Newton is 1 kilogram meter per second squared. We invented the kilogram, we invented the meter, and we invented the second, and therefore we also invented newtons. These are impositions that we imposed upon nature to say, this is what a standard unit of mass should be. This here is what a standard unit of distance should be. But humans did not invent gravity. Gravity is a fundamental force, and it's part of the machinery of the universe. So the reason that we have to do experimentation in science is because we have to ask nature, if you have 2 1 kilogram masses and you separate them by a meter, how strong does nature plan on tugging between those two things? Because gravity is a weak force at small human scales, Newton didn't have a good way of answering that question. He actually did not know how to compute a force. He could only tell you how forces would change. To do that, another physicist, another experimenter would have to come along. And that scientist was Henry Cavendish. He came up with a legendary experiment to measure the strength of gravity using something called a torsional pendulum. And perhaps this would be a clean, I just want a really clean demo here. Here's a clean illustration. Okay, he took these 2 masses of lead, which are very dense, and he attached them by a thin metal rod, and he hung the rod from something called a torsional fiber. A torsional pendulum hangs by a wire, and it kind of rotates in a horizontal plane, but it doesn't go up or down. Then he took these larger lead masses and he attached them to a bar which he could kind of slide and pivot around. Now, they were going to, in theory, have a tug of gravity on each other, but a tug that he knew would be so tiny that it would probably produce the smallest or most microscopic deflection. But he found that he could amplify that microscopic deflection by taking a light source, and in the modern version, we use a laser because it's very narrowly collimated. He bounces the light source off a mirror, and if he projects the scale far enough away, really, really tiny deflections in the mirror, tiny deflections of these masses, will create big observable changes in the laser beam once you project it on the wall. He's basically exploiting the fact that very, very tiny deflections in angle will create big displacements in distance if you project them far enough away. Very ingenious device. He actually did get the ball bearings to twist a little bit due to the pull of gravity, and he made the first measurement of what is now known as big G, the universal gravitational constant. And if we insert that into the equation, we can create the modern form of gravity, which allows us to calculate forces in newtons. So let's write that down now. The modern version of Newton's law of gravitation is that the force of gravity is equal to big G, a fundamental constant of the universe, times m1 times m2 divided by the distance squared, where big G is known as the universal gravitational constant. It's your first constant of nature. It is baked into the machinery of the universe and it does not change. The value is approximately 7 times 10 to the negative 11. It has really goofy units. The units are meters cubed per kilogram per second squared. And the way you should think about big G is kind of like an index of the strength of gravity. Let me see if I can fix, is that glare coming from my computer? Maybe if I turn the lights down a bit. That didn't work. Maybe my screen brightness. I wonder if that will show up in the video. Not really sure what the best way to do this is. Oh, apparently I've blocked the glare. Sorry, I'm just trying to figure this out. Why don't we try a sample calculation? Here, let's consider some famous astronomical objects. Let me go over to my 1010 slideshow for a second. And where is this thing? Somewhere here. What if we consider, I don't know, the Earth and the Moon and the Sun? What would you guys suspect is the stronger force of gravity? In theory, there should be a force of gravity. Actually, let's draw it this way. It should be a single force between two objects. There should be a force of gravity between Earth and the Moon. And there should be another force of gravity between Earth and the Sun. What do you suppose is bigger? The gravity between Earth and the Moon, and the gravity between Earth and the Sun?
Gravity between Earth and the Moon because the distance is closer.
It is true that the distance is shorter between Earth and the Moon. On the other hand, Caitlin, do you also agree that the mass of the Sun is probably a lot greater than the mass of the Moon?
Oh, definitely. So you would have to calculate to really know which one would be greater.
That's exactly my point. This is something that would be hard to guess without the law of gravity, because you could kind of see either argument as holding. Very, very clear-eyed of you. I love it. Okay, so in that case, why don't we be about it and we'll learn how to punch some stuff into our calculators. I need to erase this. By the way, the masses and the distance may change, but this big G does not change. That's nature telling us how hard she likes to tug on things, okay? It's the same for galaxies as it is for apples coming down from a tree. Okay, let's try this sample problem, similar to something we'll do today. It seems crazy at first, but we'll get the hang of it. Find the force of gravity between Earth and the moon. And if we kind of look up the values in the book, we will need some givens here. The mass of Earth is 6 times 10 to the 24 kilograms. The mass of the moon is 7 times 10 to the 22 kilograms. And the distance between them is 384,000 kilometers. In this problem, I gave you values the way that they would probably appear in a table, say from the back of your astronomy textbook, or in a table that you might find on the internet. However, kilometers are not MKS units. Our first step is to convert the distance to meters. That's because we're going to require meters for our formulae to work. Caitlin, would you be kind enough to help me do that?
Yeah, I can try.
That's okay, we can stumble through it together. So let's use our 4 steps of dimensional analysis here. What's our first step in dimensional analysis?
Hold on, let me find my notes.
Consult your notes.
Write down the number to convert, which would be
Wait a minute,
the
wait, Caitlin, I'm sorry, but you missed a part. There's more to that story. Did you not write anything else down except for write the number to convert?
I must have.
Did anyone else get the real deal version?
With its units.
Yeah, thanks, Caleb. You know, Caitlin, that's kind of an important part. Write down the number to convert with its units. Please put that in, Caitlin. That ain't no small thing. That's a big thing. So, Caitlin, let's proceed. What should I write down?
So the number that you have to convert is the distance, which is 384,000 kilometers.
All right. And I've learned that it's important to say the part about the units because people miss the whole point of this thing. What's step 2?
Step 2 is to multiply by the division bar.
Done. Step 3.
Put the units in first to cancel.
All right. So if we hadn't put the units in here, we wouldn't know how to cancel them out. What do we do?
Yeah. So kilometers is going to be on the bottom.
Yep.
And then on the top would be,
To go to MKS units.
would it be meters?
That's right. We're trying to convert to meters. All right. And then that's cool because now our kilometers will cancel out whoosh, whoosh, top and bottom, right? We've Indiana Jones whipped them off the board. Okay. Now what's step 4?
Step 4 is to put the numbers in second using the conversion factors needed.
So we need the conversion from kilometers to meters. I should have had you write that down last time.
Well, 1 kilometer, 1 kilometer is 1,000 meters.
Right. So which number goes where? Because it's possible to screw that up.
So would it be 1,000 meters over 1 kilometer?
That's right. We keep the number next to its unit. Sometimes 1 ends up on the top, sometimes it ends up on the bottom. It's important to be careful. Okay, you don't actually need to punch this into your calculator, Caitlin. And if we use our powers of 10, we can make this quick and dirty. How many zeros here?
3.
And here?
3.
So if we pack that into a power of 10, I could probably just write it 384 times 10 to the...
10 to the 6th power.
That's right. And we can punch it into our calculus just that way. Now, the kilograms that we were given are in MKS units. So that's cool. That means they're good to go. So now we plug it into the formula, okay? And this is the step that the physics students call plug and chug. Plug and chug means once your units are in place, you put it in the formula and you do some work, okay? So the force of gravity between Earth and Moon, E plus M. First, I'm going to write down big G, 7 times 10 to the negative 11. The units are meters cubed per kilogram per second squared. Notice that I'm writing in my units as I go here. Times the mass of Earth, 6 times 10 to the 24 kilograms, times the mass of the Moon, 7 times 10 to the 22 kilograms. And I want you to watch how I write this next part. Divided by the distance squared. I'm going to put open parentheses 384 million, 384 times 10 to the 6 meters, and then I close the parentheses and square it. I am going to be writing in parentheses here where there's a square, but I will not need to type this into my calculator. The reason I'm putting in those parentheses is because the units are also squared as well as the number. And that is not a small thing either. That square gets distributed to the number and the square gets distributed to the units. If you did not put the parentheses in, a reader could read this as 384 million square meters, not understanding that the square distributes to the number as well. It's all about just unit bookkeeping. Okay, now I'm going to teach us how to plug this in. It seems kind of nutty the first time around, but you actually can do it quite quickly. Here are some tips. We're going to punch it in one clean shot. And the other tip is we're going to use our EXP key. Because this is a little more involved, I'm going to see if I can activate my focus. Let me just try to do something here. Let me turn off the good camera. Let me activate it here. And let me change my focus to close, hold on. That's good focus. Now I'm going to deactivate it. I'm going to reactivate it here. I'm getting the swing of this now. And if I did everything right, which I didn't, it didn't work. I thought I would have like, I think it just reverted to autofocus or something. Sorry, guys. Okay. Well, hopefully if I hold it back, you'll be able to see this. Sorry. Okay. Clear it out. So first we plug in we're going to use EXP for times 10, right? So 7 EXP negative 11 times 6 EXP 24 times 7 EXP 22 divide by 384 EXP 6. First, I'm going to square it, which is up here. So squared. And then I'm going to hit equals. At the end, you should have a number that looks something like this. Looks like Lionel is, hold on. Lionel, what's that power say? You've got glare. See how I twist mine sideways to avoid the glare? Just a little twist back and forth sometimes can help. Is that 20th power? Lionel, I can't hear you.
Yes.
Okay. How about the rest of you galoots? Did you guys get it? Yep.
I look like crap. I'm not showing my face on this camera.
You ain't showing your face? Okay.
I look like crap.
That's, you know what? I disagree. But Emma, it's hard to see. Emma's using an unorthodox calculator here. So you asking for it. Emma, you're muted, so I can't hear anything you're saying.
Yeah, it's the same. It's 1.9938, continuing times 10 to the 20th.
So Emma, since we're interfacing for a second here, how should I round my final answer?
You should round it to would it be to 3 sig figs?
No. Round more boldly.
To 2 sig figs?
How many sig figs does that number have?
1.
1. Just round it to 1.
Okay, so then 2 times 10 to the 20th.
Very good. But 2 times 10 to the 20th what?
Would it be? I think would it be kilograms over seconds squared? That's what I was getting from canceling out the.
Okay, so let's say we want to play that game. You missed something though. 1 kilogram cancels with 1 kilogram, okay?
Right.
But there are, remember, you have to distribute the square to the meters as well as the number, right?
Okay, right.
So 3 meters and 2 meters at the bottom leaves you just a single meter to the 1, right?
Right.
So we have a meter, we have a kilogram on top, and a second squared on the bottom. So that's kilograms times meters over second squared. Damn, that kind of reminds me of something. That sounds like a kilogram meter per second. What the hell is that? Does anyone know? Aha.
That's
Newton.
Newton's, right?
Yeah, this is a force. And at the end of the day, forces had better be in newtons. So that's 2 times 10 to the 20 newtons of force. Now, there are 2 ways to do this. The way that Emma did it is what you do if you're getting confused. You try to balance out the units. But we could also assume, well, it's a force. So if I did things right, it better come out in newtons. Box that. That's the answer. Let's see if we can do this one more time, just to see if you guys can do it without me punching for you. All right? Does everyone have this? Because I'd like to erase. I finally got my glare thing figured out, so that's good. Okay, let's try a second problem. Find the force of gravity between the sun and the Earth. Here we have the mass of the Earth. The mass of the sun is 2 times 10 to the 30 kilograms. The distance between them is 1 AU, or 150 million kilometers. Once again, kilometers are not MKS units. We'll have to convert. In the interest of time, I'm going to do that quickly for you. I write down the number to convert with its units. I multiply by a division bar. I put my units in first to cancel, kilometers on the bottom. And then I plug in my conversion factor. 1,000 meters to 1 kilometer. 6 zeros plus 3 zeros gives me 150 times 10 to the 9 meters. That's how quick I want you guys to be. Now I will plug it into my formula. Force of gravity between the sun and the Earth is 7 times 10 to the minus 11 meters cubed per kilogram per second squared times the mass of the sun, 2 times 10 to the 30 kilograms times the mass of the Earth, 6 times 10 to the 24 kilograms, divided by 150 billion meters squared. Write it down, punch it up, and tell me your answer. First person who gets it, just give me a shout. Anyone?
Would it be, hold on, let me round it. 4 times 10 to the 22nd power in newtons.
One more time, Caitlin, because I heard a glitch there.
Yeah, that's fine. It would be 4 times 10 to the 22nd power in newtons.
That's beautiful. I like your rounding skills too. Good moves. Okay, so let's try something, Caitlin, you and me. This is the force that we got for the sun to earth gravity, right?
Mm-hmm.
And if you remember in our previous problem, we got 2 times 10 to the 20th newtons. That was the earth to moon gravity, correct?
Yes.
So what did we learn?
We learned that the Earth and Moon have a stronger gravitational pull to each other.
What?
Because of, no, it's the opposite, sorry.
Okay, first of all, when we read a number in scientific notation, let me tell you the pecking order. This is the number, okay? Not this. But either way, both the power is bigger and the lead digit is bigger, right? But honestly, the lead digit doesn't matter much. It's really just the power. So to do penance for me, Caitlin, let's compare by taking the ratio. 4 times 10 to the 22 newtons divided by 2 times 10 to the 20 newtons. No calculators here. What happens if you divide the 2 lead digits?
4 divided by 2 is 2.
And then to get the power, you subtract the exponents.
Which be times to the second power.
So what does that mean?
2 times, no, not 2 times greater. Is it?
Not 2 times greater.
4 times greater.
Wait, come. 2 times 10 to the 2 is not 2 times 2.
Oh, sorry.
Right?
Yeah.
This means a 2 followed by how many zeros?
0, so 200 times greater.
There you go. It's 200 times greater. In other words, the gravity between the sun and the earth is 200 times greater than the gravity between the earth and the moon. Now, I want you to think about something for a second. What causes tides on Earth?
The moon.
The gravity of the moon.
Why doesn't the sun cause the gravity? Oh, why doesn't the gravity of the sun cause tides if it's 200 times greater?
Because it's a lot farther than the moon.
But didn't we account for distance when we plugged into our law of gravitation, right? Like when we did the force of gravity, we plugged the larger distance to the sun in and the shorter distance to the moon in, but the sun still beat out the moon in terms of gravity because its mass is a 2 followed by 30 zeros. How is it? I mean, gravity, the tides are causing gravity, right?
Yeah, that's confusing.
That's pretty weird, right? It's not your fault that tides are actually really complex and they come up in our homework today. So I'm kind of out of time, but I've got just like another 5 minutes before a break here. Let's see if we can squeeze in one last mini module on tides. I'll try to keep it short and sweet. But tides are confusing and we have a question on them today.
Teach me anything. I'm down to learn anything that has to do with this. You never know when you're gonna need this.
That's what I want to hear. This is interesting stuff. So it's not, in my opinion, it's not boring stuff. Okay, so let's learn about something in physics called the tidal force. Here's the easiest way to describe this. Let's start with this bullet point. Yes, tides are caused by gravity. But, ... the tidal force, as it's called in physics, is not exactly the same as the gravitational force. Here, I'll try to define it, but there's going to be some buzzwords. The tidal force is a differential force. And a differential force, okay, Amanda, catch up on this video and watch the homework later. It's pretty intense. It's a differential force, which means a delta force, a change in force, caused by gravity acting over an extended body. In other words, the tidal force is a change in force between the force of gravity that acts, say, on the front of a body, subtracted from the force that's acting on the back of a body. And because if you analyze this from the point of calculus, this is a gradient. Another way to say this would be it's a gradient of force. Unlike gravity, the tidal force ends up having a proportionality of 1 over the distance cubed. And that means that even though the moon's gravity is weaker, its closer proximity creates a greater difference between the front tug of the moon versus the back tug of the moon. So in other words, just to do this kind of quickly, and I'll let you guys. David's doing a little dance here. In other words, if I were to go back to that other slideshow and just use it as a little diagram here. Excuse me. If you look at the gravity of the moon, it's tugging stronger on the front than on the back. Well, the difference of force changes. Actually, you know what, guys? I'm gonna do something here. If it's okay with you, I'm going to leave this up and we're going to pause our lecture or stop our lecture here. And I'll pick this up next time because I know our homework is, I know if I get into that discussion with the diagrams, I'm going to go off for a spell. And I think I'd rather pause, end the lecture here, and take a little 5 or 10 or 15-minute break. And then when we come back, we're going to beast out the homework. Would that be acceptable to everyone? Okay. Thank you. I need a little break here. So my current iPhone time is 12:57. Let's say at 1:15, we'll get going on things. That should give everyone enough time for a quick snack. Okay. All right. I'll see you guys in a few. Okay, everyone. Let's get to work on homework number 3, which covers chapter 4 from the book. We'll begin in the usual method. We'll have our name, AS1020. Please list your section, 001, 102 for the night class, 600 for the online class. Make sure we identify this as homework number 3, chapter 4, and let's grab us some numbers. Let's see here. Okay, looks like we got 45, 47, 56. Looks like we got, I don't think I want to do D, E, F. I think today I want to do 57D and 58A. I think that's the plan. Because we haven't introduced those formulas, we'll try them anyways, but we won't go nuts. So that's a slight deviation from what it lists there. That will be fine. This is the official homework 3 that we'll do today. It'd be great if I can get you guys to open up the questions and read for me. That will allow me to write the givens down. We can right-click this chapter 4 PDF. And if you do that, you will see a, come on, you dork. What's going on here? Oh, there we go. You'll see a PDF, a scan of the questions. And our first one is 45. Emma, you're on the top of my list. Could you be kind enough to read that? We're going to be using the Newtonian version of the law of gravity. Force is directly proportional to the product of the two masses, inversely proportional to the square of the distance. Do you have those questions handy, Emma?
Sorry, I was muted. Yeah, so number 45, the gravitational law. How does quadrupling the distance between two objects affect the gravitational force between them?
Okay. So by what factor are we changing the distance?
By 2.
Quadruple?
Oh, sorry, by 4.
4, right. So we're changing the distance to 4 times greater. Well, hold on. Let's just say 4 times. So how do we write our proportionality law here? we should only consider the factors that are changing. The force of gravity is proportional to what?
The mass of the first object times the mass of the second object over distance.
Hold on. We're not varying the masses, are we?
Oh no, it would just be.
So we don't need to include the mass for this part. We include force is proportional to. We're interested in how does this affect force?
So would we just write 1/4 squared?
Yeah, but first let's write it as 1/d squared. Let's write, because what we're emphasizing that we're focusing on the distance, right?
Right.
So force is inversely proportional to the square of the distance. We're not varying the masses. And yes, now we substitute 4. We write it again. This time substituting in 4 squared. Now we turn it into an equals. So what's 1/4 squared?
1/16.
Yeah. The new force is 1/16. The old force, or put simply, 16 times weaker. What's question B?
Hang on, I'm just writing down the answer.
Sure, when you're ready.
B is, suppose the sun were somehow replaced by a star with twice as much mass. What would happen to the gravitational force between Earth and the sun?
So here we would write force is proportional to what?
As proportional to mass?
To one of the masses. We'll say
Right.
M1. And M1 is varying by a factor of 2. So the new force is 2 times stronger. Part C.
Suppose Earth were moved to 1/3 of its current distance from the sun. What would happen to the gravitational force between Earth and the sun?
Okay, so how do we write our proportionality argument? I can see that I'm going to run out of space here, so I'm going to erase all of this. Force is proportional to what?
Distance?
No, force is not proportional to distance. If you say force is proportional to distance, that's what that means. Clearly, that's not the relationship between distance and force. Try again.
1/distance squared.
That's better. Inversely proportional to the square of the distance. And by what factor are we changing our distance?
1/3.
So we have to substitute in 1/3 for D. But the 1/3 should be in parentheses because we want to square all of the 1/3. Distribute the square. What do you have?
9.
Yeah, it's 1/1/9. The bottom of the bottom fraction flips up to the top. The new force is 9 times stronger. And that covers question 45. Vincent, once you're ready, I'll ask you to read the next one, chapter 4, number 47.
Number 47. The
Hold on a
title.
second. Oh, wait, Vincent, to
Yeah.
everyone else, I'm going to erase this. So complain now. All right. Okay, I'm ready for you now, buddy.
All right. Number 47. The title is Head to Foot Tides. You and Earth attract each other gravitationally, so you should also be subject to a tidal force resulting from the difference between the gravitational attraction felt by your feet and that felt by your head, at least when you are standing. Explain why you can't feel this tidal force.
So this is not about the moon in any way. This is about the gravity of Earth. Draw a medium to large size circle. Put a person standing on the top of Earth. And then draw in the radius of Earth like so. The radius of Earth is 6,400 kilometers. How tall is a typical human being to one significant figure?
Like 2 meters.
Beautiful. David, do you know what 6,400 kilometers is in meters?
Don't. Would we have to convert that?
Sure. Here's a division bar. Put some units in.
So you would put kilometers on the bottom and meters on the top.
What's my conversion factor?
Would it be 1,000 to 1?
That's right. Now, without using your calculator, let's count our zeros. Ready?
6. 3 and then 5.
But then if we're going to move the decimal point, we should treat the 4 like a 0 too. Okay. So 6.4 times 10 to the
6th
meters. And here, 10 to the power of 6, what is that in plain English?
Million.
Right. So a typical man is 2 meters tall. The radius of Earth is 6 million meters tall. Now, when we talk about a tidal force, they mean to say that you're made up of a bit of fleshy, you're made up of a whole collection of fleshy bits, right? Your feet, if you were to cut them off, would have some mass. And your head, if you were to cut off your head, that would have some mass. So what they're saying is the Earth's gravity, which acts sort of as a point source at the center of a big soap bubble, there should be a force of gravity acting on your feet. We'll call that force F sub foot. And there should be a force of gravity from the Earth acting on your head. We'll call that F sub head. And in theory, if your head is 2 meters farther from the center of Earth than your feet, there should be a microscopic difference in the force between your foot and your head. And it asks us, why don't we feel that force? What's the simple answer to that question?
It's microscopic.
What is it?
The gravitational force between your head and your foot.
But that sounds like the gravity between your head and your feet.
Oh, I meant like what I meant to say is the difference
Yes.
between your head and your foot. Yeah.
The difference between the foot Earth gravity and the head Earth gravity. But David, I was with you when you said difference in force. That's the key phrase, okay? So let's write it out like this. The trick is to use some of those vocab phrases that you had a moment ago when I described tides, but also to kind of compare these two distances here. A person will not feel a tidal force acting across their body from Earth so the tidal force would act across their body from Earth because the 2-meter height of a person is quite literally millions of times smaller than the radius of Earth. Therefore, the difference in force, and I'd like you to underline the phrase difference in force. Let me make that a little clearer here. The difference in force between Earth's gravity on your feet and Earth's gravity on your head is essentially 0, although in theory, not quite 0. All right. Quick and efficient. We love it. I'm ready to move forward when you guys are. Please include the diagram. I'm erasing. Chapter 456. David, care to help?
Understanding Newton's version of Kepler's third law. Find the orbital period for the planet in each case. Hint, the calculations for this problem are so simple that you will not need a calculator.
That is absolutely not true. All right, what's it ask of us? Let's go up here.
Was that A? Oh, yeah, I see it. A planet with twice Earth's mass orbiting at a distance of 1 AU from a star with the same mass as the sun.
Okay. Unfortunately, guys, I didn't quite get to this very important formula, although I was just about to, but there just wasn't enough time. That's okay. We can still muscle our way through it, and I'll teach it to you next time. This formula is known as Newton's version of Kepler's third law. Newton's version of Kepler's third law is such a lot to say that y'all sometimes I just refer to this this equation as NK3. And basically, if you remember, Kepler's third law, which you only learned in your last lecture, was p squared is equal to a cubed. Unfortunately, Kepler's version only worked for planets that orbit the sun, but Newton came up with a better version that included gravity, so he could use it for any two orbiting bodies, for instance, the moons of Jupiter. And his version is 4 times pi squared times a cubed divided by big G times the sum of the masses in parentheses. This version is called Newton's version of Kepler's third law, NK3. It's important to note that unlike Kepler's, which used years for period and AUs for the distance, here, these are all MKS units. So periods must be in seconds. The distances must be in meters. The masses must be in kilograms. Might even be helpful to draw a little picture of what's going on here. You can just imagine that you have two masses like the Earth and the Moon, M1 and M2. The distance between them is now A for semi-major axis, but it's basically kind of like the radius of a circular orbit. And then M2 is orbiting around M1 with some kind of a period. Once again, I'll talk more about this equation next time, but today we'll just kind of plug in some numbers and see what happens. Okay, I'm going to erase because I need my board back. Part A. I've already forgotten. It was a planet with twice the mass of Earth orbiting at a distance of 1 AU from a star with the same mass as the sun. So here, our givens are 1 times the mass of the sun. I'm going to use this symbol for the sun. It's from it's actually from an old astrological symbol. It's a circle with a dot in it. The Egyptians invented it. So 1 times the mass of the sun, 2 times the mass of Earth. Earth is a circle with a cross in it. And the distance is 1 AU. So let's remind ourselves that the mass of the sun is 2 times 10 to the 30 kilograms. the mass of Earth, 6 times 10 to the 24 kilograms, one AU is 150 million kilometers. And if you'll allow me to speed things up, because this is a kind of lengthy operation here, I'm quickly going to convert from kilometers to meters, just like we did in today's lecture. Use dimensional analysis, put kilometers on the bottom, meters on top. 1,000 to 1 is 150 billion meters. I did that rather quick compared to you guys, so watch out for that. Okay. Let's write Newton's version of Kepler's third law, but this time let's solve for the period by square rooting both sides. The period of the Earth would be the nice big neat square root of 4 times pi squared times a cubed, where a is our distance, divided by big G times 1 times the mass of the sun plus 2 times the mass of Earth. At this point, we could plug in this value, and this value for that, and that. But if we did that, we would actually miss a little trick or a little secret. Sometimes it's easier to kind of refer to this quantity in parentheses as the total mass. And I'm going to ask us to calculate the total mass separately. Oh, I'm going to do that up here because I'm out of board space down there. The total mass would be 2 times 10 to the 30 kilograms plus 2 times 6 times 10 to the 24 kilograms. You guys think you could handle punching that into your calculator? What'd you get?
You want us to round to 1 sig fig?
Sure.
So 2 times 10 to the 30th.
Hold on, Emma, wasn't that just the mass of the sun?
Yes.
How did you add the mass of the Earth and just get the mass of the sun again?
Well, if you want me to round to 1 sig fig, then the mass of the Earth would be insignificant compared to the mass of the sun.
That is my point. This is a trick. You have to be able to know to play this trick. Sometimes the mass of a planet usually is too small to actually count. So you can ignore the mass of the planet because the sun is so much bigger. It's approximately just the mass of the sun. Very good. So I'm going to erase and I'm going to rewrite this whole thing again, substituting our values. I'm going to erase down here now. All right, the period, make a nice big neat square root, 4 times pi squared times open parentheses 150 billion meters cubed to the power of 3 divided by big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared. Times the mass of the sun, 2 times 10 to the 30 kilograms. Now, Emma is going to be doing things weird with her calculator, but anyone who has a Casio calculator, let's talk this through. We are going to punch in all of this stuff first, and after we hit equals, we're going to do the square root. The key trick is this part right here. When we get to this part, we will not hit times, we will hit divide, so that the calculator knows this number and that number are both in the bottom. See if you can follow along with me, because this can be a little nutty. 4 times pi, which is just exp, and then squared, times 150 exp 9. We have to cube this. So I'm going to do shift, and that button is cube. So you have to do shift cube divided by 7 exp negative key 11, and then divided by 2 exp 30. First, we hit equals. You'll see some big number times 10 to the 14. Now we have to square root this. Shift square root. And there is the answer we should have. If not, we're going to have to talk. How should I round this? Let's do 2 sig figs.
Would it be 31?
Okay. Times the what?
Ten to the 6th?
And the units?
Kilograms?
Kilograms cancel. Top and bottom.
Oh, yes.
What else? Anyone?
It would be mass.
Mass have units of kilograms, but kilograms cancel out.
Second squared.
Oh,
Second, sorry, because there's a square root.
Right, because it's you end up with the square root of 1 over seconds squared. That's the square root of seconds, which makes sense because it's a period. So it's either 3.1 times 10 to the 6 seconds, sorry, 31 million seconds, or you could do 3.1 times 10 to the 7 seconds, whichever one you prefer. That's our answer. However, to understand what the answer means, let's convert this to years. 3.1 times 10 to the 7 seconds. In your previous lectures, I gave you a conversion factor from seconds to years. Do you remember what that was? I gave it to you under MKS units last class.
It would be 3.15 times 10 to the 7 seconds.
And where do I put that?
On the bottom.
And what goes on the top?
1.
Okay, now punch it in.
Wouldn't that be roughly a year?
Huh?
Wouldn't that be roughly a year?
Yeah, of course it would. Duh. Of course it's going to be 1 year, because you have a planet orbiting the same mass as the sun at a distance of 1 AU. The mass of the planet is insignificant, so it should have the same period as our own planet, 1 year. That's why they said this problem is so simple you won't need a calculator. But I think you guys needed to do this out the hoary-gory way. That was part A. Now we're going to do part B. Going to erase. Okay. Who is my reader?
With me.
David, can you tell me what B says?
A planet with Earth's mass orbiting at a distance of 1 AU from a star with 4 times the sun's mass.
Okay. Last time we worked out that 1 AU was 150 billion meters. Here, the total mass is 4 times the mass of the sun plus the mass of Earth. Can we simplify that?
Four times the mass of the sun.
Yeah, we can neglect the mass of Earth. I just wanted to make sure that you guys remember that the mass of Earth won't matter. The mass of the sun certainly will. All right. This time we're going to plug it in. P equals the nice big neat square root of 4 times pi squared times 150 billion meters cubed divided by big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared, times 4 times the mass of the sun. Here, plug this in, divide by G, divide by 4, divide by the mass of the sun. Do you guys want to see if you can do this without my help? Last time I showed you how to plug that in. I think it would be pretty cool if you guys could just do that. That's how I want to eventually get to the place where I don't have to show you the calculation every time. You can just punch it and crunch it for me. Let's see how badly that goes. Everyone punch it in and show them what you get. Hold up your calculators or something. Oh. Let me know when you got something.
I got 3.8 times 10 to the 15th.
No.
Okay.
Okay. So let's try this together, okay? 4 times pi squared times 150, sorry, Mikey, no good. exp9 shift cube divided by 7 exp negative 11 divided by 4 divided by 2 exp 30 then equals, that's right, Emma, then shift square root. You get it, David? People have to usually punch this a few times before they learn the secret. Yeah, that's not square, it's square root. You cube there, you hit equals, and then you square root. Okay, Emma, what did you round it to?
1.5 times 10 to the 7 seconds.
And let's convert that to years together. What's my conversion?
It's, sorry, I'm just writing it down, the equation. It's 1 year to 1.15 times 10 to the 7.
Not 1.15.
Or sorry, 3.15 times 10 to the 7 seconds.
So? So?
The
screen seems dark.
Oh, it's about 1/2.
Huh?
About 1/2.
Yeah, it's actually exactly 1/2. This is pretty interesting. This took a lot of work to do. Well, sort of seems like a lot of work. But we could have actually accomplished the same thing much quicker had we had the power of proportionality arguments. For instance, had we, the cat is scratching the rug because it's hungry and it's pissed off. Okay. If you had been good at proportionality arguments, we could have done this a different way by saying p squared is proportional to a cubed over the total mass, right? The a didn't change. We're still at 1 AU. But the total mass changed by a factor of 4. But if p squared is proportional to 4, then p would be proportional to the square root of 1/4. And the square root of 1/4 is 1/2. The new period is half the old one, which is what we found through a longer means. In general, this is the way that you need to prove it to yourself and start doing things. But with proportionality symbols, you can figure stuff out much faster. This concludes number 56. Mikey, when you're done writing, are you down to do a reading? Mikey, my friend? Mikey? Talk to me, buddy.
He talked in the chat. He said his mic isn't working.
Oh, bloody hell. Okay, Emma, can you do it for me then? Sorry. I'm erasing.
Something nice, and I get dragged into all this.
I'm sorry, say that again?
I was joking. I said I tried to do something nice, and I just get dragged in. Like,
That's right. Well, I'm trying to do something nice too, which is help you solve your homework quick and fast, right? So let's help each other out.
all right. So 57. We're just doing 57D, right?
Yeah, but read whatever stuff is. What's the title?
Using Newton's version of Kepler's third law.
Okay. In this particular case, if I think I remember what happened, what's the problem for D again?
Calculate the combined mass of Pluto and its moon Charon.
Okay. So the point of 56D, before you read anything, is we're going to use a new version of NK3. It's the version that's solved for mass. And this is the actually useful version of NK3, believe it or not. It's that the total mass of a system, in other words, M1 plus M2, if you solve the equation for that, NK3 now becomes 4 pi squared times A cubed over GP squared. This is a really important formula in this course. NK3 solve for mass. And this is why you're learning this formula, because this is what astronomers use it for. They sometimes call it the cosmic balance beam, because this is how astronomers measure the masses of big things like stars and planets. In question D, they want us to find the combined mass of Pluto, and it has a moon called Charon. And now I'll ask Emma, what are the givens here?
From the fact that Charon orbits Pluto every 6.4 days with a semi-major axis of 19,700 kilometers.
All right. Any thoughts about how we should start this thing? Did you feed him? Sorry, I had to pet the cat. Okay, so what do you think? What do I do?
We'd have to convert days into seconds.
That's right. So let's convert the period to seconds. 6.4 days. What do I do with dimensional analysis there?
You multiply it by a division bar with days on the bottom and seconds on the top.
Do you know the number of seconds in a day? Off the top of your head?
No.
If you don't, then maybe you should go to another unit that'll get us closer to seconds and we can leapfrog a couple of times.
So we could do hours.
Okay. And let's just set everything up with our units first. Then we'll do another division bar. That'll cancel days. Then what do we do next?
We could convert hours to minutes. So you'd have hours on the bottom and minutes on the top.
Yep. And then what?
And then minutes to seconds, which would be minutes on the bottom and seconds on the top.
Good. Notice that I like to get all my units in place before I mess with any numbers. That's a pro tip. Okay, Emma, can you supply some conversion factors?
Okay, so for days to hours, it's 1 day to 24 hours.
Where does the 24 go?
On the top.
Okay, next.
And then for the next one, 60 minutes, so 60 on the top to 1 hour. And then for the last one, 60 on top and 1 on the bottom.
Okay, punch them up. Tell me what you get. Keep at least 2 sig figs.
552,960.
Oh my God, way too many sig figs. Please round that.
Do you want 1 sig fig or 2 sig figs?
2 sig figs.
5.5.
I don't need scientific notation. It's not really.
Okay, so just 550,000.
Is that what everyone else gets? Seconds, right?
Yeah.
Okay. Now we should convert our distance to meters. Vincent, can you help me do that? Vincent, baby.
Yes, yes.
What's our first step?
Write down what we need to convert. So 19,700 kilometers.
Lovely. Now what?
Multiply it by a division bar.
Now what?
And now write in the units, just the units. So
I like the way you talk.
So kilometers would be on the bottom and meters would be on the top.
Step 4.
Put in the numbers.
Hit me.
Along with the units using conversion factors. So kilometers, it'll be 1 kilometer on the bottom and 1,000 meters on the top.
Can you do that without a calculator? I'll get you started. 19.7 times 10 to the what?
6.
Right.
Or no. All right.
Sorry? Yes, 6 times 10 to the 6.
6.
Units?
Meters.
And that's our A for the equation. So we have P, we have A, we know G, we know pi. We're ready to plug this stuff in and have a party. I will have to erase the conversions, however, because I'm out of board space. I'll just give you a second to catch up. Okay, I'm going to erase. So the total mass of Pluto plus Charon will be 4 times pi squared times 19.7 million meters cubed divided by big G 7 times 10 to the minus 11 meters cubed per kilogram per second squared times open parentheses 550,000 seconds squared. Here, in the interest of time, I did not put units in friendly colors. What are the chances that you guys could pull this off without my help? Probably slim. I'm guessing you guys still need some practice. Because there's definitely going to be someone out there in the studio audience who struggles, I'll punch you through this with my calci, okay? 4, I wish I could show the equation in my calculator like that. Okay, 4 times pi squared times 19.7 exp6, gotta cube that, shift cube divided by 7 exp negative 11. Now I have to hit divided by, because that's on the bottom, 550,000. I have to square it, badoink, and then I have to hit equals. Let's round it to 2 sig figs. What's my final?
1.4 times 10 to the 22nd seconds.
It was seconds when we were solving for period, but now we're solving for the combined mass of Pluto plus mass of Charon, right?
Oh, okay.
Also, the units don't work in the same way. Meters cubed, take a look. Meters cubed cancel, seconds squared cancel.
So it'd be kilograms.
That's right, which makes sense because it's a mass. Box that up. Boom, 57D done. I know this is a bit of a crunchy homework, but it's just because you're not practiced. Pretty soon it won't be so hard. Okay, we got one more to do, 58A. David, I guess I'll have you read it, but let me set up a little pregame work, okay? I'm erasing. So all these last problems kind of involve formulas I didn't quite get to. The last one is a pretty straightforward equation. It's called the escape velocity. The symbol that we're going to use is V for velocity, subscript escape velocity. V subscript ESC, okay? The escape velocity is that speed you need to escape a planet or star of mass m and radius r. That speed you need to escape a planet or star. Why am I not plugged in? Holy shit. Oh, gosh. Wow. I can't believe this guy. I was wondering why my screen was so dim. It was because I was plugged in here, but I wasn't plugged in over there. Oh my gosh, that could have been a disaster for this video recording. The escape velocity formula is the square root of 2 times big G times the mass of the planet divided by the radius of the planet. What do they want us to do, David? Once you're done writing, tell us about part A.
So escape velocity, calculate the escape velocity from each of the following using data as needed from Appendix E. And for A, it's just the surface of Mars.
So we need the mass of Mars and the radius of Mars. The mass of Mars is 11% of Earth's mass. The radius of Mars is 53% Earth's radius. That makes 3,400 kilometers for the radius, and 10% of Earth's mass would be like 6 times 10 to the 23 kilograms. We got to convert the kilometers to meters. In the escape velocity formula, masses are in kilograms. The radii are in meters, but I think you guys are getting pretty good at the conversion so far. It's kilometers on bottom, meters on top. And so far, at least the people who are contributing to this discussion have seemed to grasp that there's 1,000 meters per kilometer. That gives us 3.4 million meters for the radius of Mars. Okay, thus the escape velocity from Mars is the nice big neat square root of 2 times big G, 7 times 10 to the negative 11 meters cubed per kilogram per second squared, times the mass of the planet. And Mars is 6 times 10 to the 23rd kilograms, divided by the radius, 3.4 million meters. Let's try as an experiment. Let's see if you guys can get that without any help. And then maybe I'll demonstrate after. Let's see what the 4 of you can do. Mikey, I hope you're punching too, because I haven't really, you know, I know you don't have a microphone, but.
Can I get my answer?
Oh yeah, please. That's awesome.
I got 2,182.8, so on.
You got 2,000?
Yeah.
Try again. Which way did I do this before that worked?
Is it 5,000?
That sounds better, yeah. Before I had gotten this so that, here. 2 times 7 exp negative 11 times 6 exp 23 divided by 3.4 exp 6 equals first, then shift square root. So if you have 4,970, yeah, that rounds to about 5,000. What do you think the units are?
Would it be meters squared second squared?
But there's a square root, right?
Oh, yeah.
That's great, Mikey. That means we're winning. All right, we're getting better. I like it, buddy. Because look, meters cancels with this, making meters squared. Kilograms cancels. The square. What is the square root of meters squared per second squared?
Just meter second.
Wait, meter times seconds? Seconds are on the bottom of the top, right?
Yes.
So my final answer, Vincent, would be, Vincent, when you say meters seconds, this is what I think you mean. Is that what you mean?
Yeah.
No, that's not a velocity.
Okay. So then would it be meters over seconds?
That's right. That's a different thing. Meters per second. Now, it's customary to convert this to kilometers per second. Anyone think they could do a quick conversion to kilometers per second? How many meters per kilometer? Thousand. That makes this 5 kilometers per second. Ooh, I like your pooch, Emma. Tell me about that guy.
This is Princess. I pick her up because my other dog decided to pee in my doorway.
Don't you just love living with
Wanted
animals?
to make sure that she didn't walk through it.
Oh, she truly is a princess.
Oh, yeah, I know you really don't want to be here right now, but you kind of have to. I'm sorry. Love you.
I love that little doggy. Okay, well, we just finished, so Princess, you can get on to taking care of her. We definitely rushed through that so I could keep the video short, but we're gonna all need some practice on this stuff, okay? All right, you guys are pretty good. Thanks for playing homework 3 with me. Next week, we'll do some more work and we'll practice. Hold on, let me give one last look at this for anyone who needs it. Okay. Next week, we'll be doing some more practice with Newton's version of Kepler's third law. I'll have a little lab on that next time, okay? So please make sure you submit. You're welcome, Mikey, you too. And please submit your lab 3 and homework 3 this week by Sunday. And I'll be hitting you guys up on Tuesday, okay? So peace out.